welcome to this month's webinar. So we are very happy to have Rebecca Willett as our speaker today. So Rebecca is a professor of statistics and computer science at the University of Chicago, where she's also the director of AI at the University of Chicago Data Science Institute. So Rebecca got her PhD in electrical and computer engineering from Rice back in 2005. After that, she joined the faculty at Duke University first as an assistant professor of electrical and computer engineering, and eventually obtained tenure at Duke. In 2013, she moved to the University of Wisconsin-Madison, and then in 2018, she moved again to the University of Chicago, where she has been since then. She works on topics that kind of combine very exciting areas of machine learning, signal processing, statistics, mathematics, and optimization. So really interdisciplinary interest in those topics. And her kind of the theme for her work is to leverage and learn hidden structure in large data sets. And such hidden structure arises in multiple applications. So she has worked in a lot of applications involving data from science and technological situations. She has, for example, worked on national security, medical imaging, material science, astronomy, and climate science, among many other things. And today we will hear about that last topic. So the title for today's talk is Machine Learning for Inverse Problems in Climate Science. Rebecca, please go ahead.
Great. Well, thank you so much for that kind introduction, and also for having me join you here today. I'm really excited to be a part of this series and to tell you about some of the stuff that we've been doing. So like Mikhail said, I'm going to talk about some applications in climate science, but to get it started, I'm going to talk about something that seems pretty far removed from climate science. So some of you may have had a CAT scan or a CT scan in the past. And if you don't know how it works, it's something that's kind of simple to explain. The basic idea is that X-rays are shot through your body from one side to the next. And what a sensor will measure at the other end is how much of that X-ray energy was absorbed. And you would measure that for each of the different X-ray beams. And so this white line here would be an absorption profile. And what we can do is we can plot that absorption profile sort of like as this column here, where dark means low absorption and white means high absorption. And as you lay in the scanner, this whole apparatus rotates around you, and we measure this absorption profile for lots of different angles. And we can plot each one of them in succession and get this object here that's called a sinogram. So this is the data that's actually measured by a CT scanner. And what is happening in a clinic after this data is collected is that computers are used to take this sinogram and map it to an image that a radiologist can look at and use to do diagnoses, etc. So one question that people have been considering for the last several years is whether we can use machine learning methods to help us with this process of reconstructing images, to train a neural network to go from the sinogram to the image, and hopefully do a better job or a faster job than classical methods. And so the naive first pass approach here was to simply train a neural network to input a sinogram and output an image. And it turns out that this is possible. You can make this work, but really only if you have a huge amount of training data. And the reason that a huge amount of data is required is that basically we have to learn two things from the data here. First, we have to learn something about the structure or the geometry of images that we want to reconstruct. But secondly, we have to learn something about how that geometry or how those images are related to sinograms. And that second thing is something that we already know. And so what we're doing with this sort of naive approach is forcing a network to learn not only the things that we don't know how to model, but also stuff that we not only know, but carefully engineer. And that requires us then to use a lot more data to fulfill this significantly more challenging learning task. So while I've described this problem in the context of CT or computed tomography, there's actually many, many settings in which we have both training data and physical models, either models of how our sensors are collecting data or models of the underlying physical phenomenon. So things like seismic imaging, climate forecasting, even molecular structure estimation are all areas where we not only have the ability to collect lots of training data and hopefully learn from it, but where also we have some knowledge of the underlying physics. And so the main claim that I would make is that physics-based models can inform the way that we design neural networks, the way that we train them, and ultimately result in methods that are more reliable, more efficient in terms of both computation and in terms of data, and sometimes even more interpretable. And so we're going to see this basic idea manifest itself in a few different settings. Just to set the stage, I want to talk just a tiny bit more about this computed tomography problem, just because it's pretty visceral. But the general idea of solving an inverse problem like this using machine learning has got widespread applications, including with a lot of different climate settings. So in this imaging context, we can model our observations, this sinogram Y, as a linear function of the image X plus some noise epsilon. So H here now is what we call a forward model. And what it's doing is it's telling us how the CT scanner works. It's basically representing that information that I showed you in the video about how we collect absorption profiles and form a sinogram. But this is a generic model that works not just for CT. The same kind of model applies in problems like MRI, in painting, removing blur, figuring out how to fill in missing data from when you have only limited sensors, compressed sensing, and a variety of other problems. So in all of these settings, the basic setup that we're considering here is one where we have a training data set that's got different XI, YI pairs. So the XI would be the image and the YI would be the observation, say the sinogram in the CT setting. And all of them have the same underlying physical model. So for all of them, for instance, YI is HXI plus epsilon I. So what we want to do is use that training data to train a machine learning model. So for instance, we could have a neural network that I'm going to call F sub theta. And I can think about this as a function where I input a sinogram or some data YI and output an image XI hat. And what I want to do is I want to choose the parameters of that model, say the weights of the neural network, for instance. So what I might do is I might say, well, I want to choose the weights that minimize the sum of the squared errors for each one of the images in my training data set. And once I've learned that network or learned that model, then when I get a new sinogram or a new set of measurements, I can plug it in and get an estimate of the image. So this is the very generic framework. And the question that I would pose is whether it's possible to design our neural network F theta, or more generally a machine learning system, to reflect our knowledge of the underlying physics. And in this particular example, what I mean by that is to reflect H, so that we don't have to learn everything about H from the data. And the answer is yes. And just like Mikhail said when he introduced me, this is, I find, very satisfying because it's not a totally ad hoc process, but rather we can leverage lots of knowledge coming from the statistics and applied math and signal processing communities about how to approach various inverse problems. And in particular, if we think about, well, what would be a classical approach to solving an inverse problem? What we might do is we might say, the way I'm going to choose an image estimate is I'm going to search over all possible images. And I'm going to try to find one that, first of all, is a good fit to my data. And I measure that using, obviously, the data, but also using knowledge of the forward model. But in many problems, there might be many images that are good fits to the data, or we might be very sensitive to noise. And so we add to this a criteria that we want to have a small value for some regularization function. And classically, this regularization function might be that the image is smooth, for instance, in which case you would have something like a ridge penalty, or that it's sparse in something like a wavelet basis, or has small total variation, or any number of different mathematical models we have for the structure and geometry of images. So this is what we would do if we knew of a good regularizer up front. And in fact, this is basically what a lot of commercial medical imaging systems and other kind of inverse problem systems are doing exactly. So when we think about trying to use machine learning as an alternative framework, what we could do is we could say, well, instead of choosing this regularization function a priori based on smoothness models, geometric models, some sort of prior probability distribution, et cetera, can we instead learn a regularizer using our training data? So let me give you a flavor of what this might look like. So up at the top here, I've got the same objective function that we talked about before that would take in some data y and output an image estimate x hat. And if I had a regularization function r, and I wanted to solve this optimization problem, then there's a variety of different methods out there, but the one I'm going to highlight here is something called the proximal gradient algorithm. And the idea is pretty straightforward. So you would just alternate between two steps. And the first step, I'm going to call it a data consistency step, because we would take our current estimate and we would perturb it a little bit to be a closer fit to the data using our data and that forward model H. And we can think about this step as basically a step in the direction of the negative gradient of this first part of our objective function. Now, once we've done this, we might have added some noise or some artifacts because this inverse problem could be ill-posed. And so in the next step, what we do is we use our regularizer to remove those artifacts and perturbations. So formally, this is called a proximal operator, but informally, it looks very much like a denoising problem, where we're taking that intermediate estimate and trying to remove noise from it using our regularizer. And I can even kind of write this using a block model like I have at the bottom, where we're alternating between data consistency and regularization, and repeat this until convergence. So this is what I would do if I knew how to regularize my problem. So instead, if I wanted to learn a good regularizer, I could use a framework called deep unrolling. And the basic idea is that we're going to replace that formal proximal operator with something that does the denoising, a learned denoiser, in this case, a convolutional neural network. And in our block diagram, I'm just replacing the regularizer in each block with, in this case, a neural network. And when people talk about deep unrolling, what they mean is that we set in advance how many different blocks or iterations we're going to have at some number k, and typically k is on the order of 5 to 10. And then we train the weights of this neural network in an end-to-end supervised manner. And what I mean by that is I have the output x hat of this whole big pipeline, and I try to make sure that that x hat is a good approximation to the true x for each one of my training samples. So the reason that I think this is really interesting and exciting becomes evident if we start to zoom in on this. So at the top, I've got this block diagram again. And if we think about what the data consistency step is doing, well, it's got this sort of formula down here that we derived using that proximal gradient algorithm. And we can think about that as itself a very simple one-layer linear neural network, where the architecture and the weights of that network are determined by our physical model, right? So H here and Y are both playing a role in determining what all of these weights in this network are. And so when we have this overall deep unrolling block diagram, what we can do is we can think about it as just one giant neural network, where some elements of the network are fixed and their weights are fixed, and they're just a simple function of what we have. And other weights are not fixed, and they are learned from our training data. And so through the lens of inverse problem solving and optimization, we were able to come up with basically this totally new architecture for a neural network that is explicitly designed to incorporate our physical knowledge. And so basically, by using not only these physical models, but inverse problem methods and optimization theory, we get kind of new insights and new architectures. And these can be really effective in practice. So here's one example with MRI reconstruction. So on the left, we've got a true image. In the middle, we've got the reconstruction with a machine learning method. And on the far right, we've got the output of a classical method. And in terms of PSNR or accuracy, they're pretty comparable. But what we can see is that by leveraging these learned ideas, we were able to come up with something that can be computed much, much more quickly, making it viable for real-time updates or much higher throughput scenarios. Okay, so I know I've talked a lot about medical imaging now, but I do want to emphasize that all of these ideas really translate to any kind of linear inverse problem setting. And so what I'd like to do now is to transition to talking about some settings that are much more specific to climate science. But where we're going to see the same kind of core ideas show up again and again. Actually, before I go into that, are there any questions so far?
I actually have a quick question.
Sure.
Yeah, please go ahead.
If you go back just a couple slides, yeah, right here or here, either one works. You talk about incorporating the physics into the node, but I guess I was missing how. I guess in the next slide you specifically talk about holding some nodes or some networks as or nodes in the network, I think, as const or fixed, and that
The weights.
the weights, yeah. Sorry, thank you. I've been using nodes too much in my the word nodes too much in my current research. My confusion is, how do you know what those node values when held fixed are? I think I just missed this.
Oh, no problem at all. So what I did is, to start with, I started with this proximal gradient algorithm that told me I should be alternating between two steps, one that's the data consistency step that uses the forward model, and one that's not. So I've got this explicit equation. Nothing here needs to be learned because this really doesn't depend on my regularizer, the thing I don't know at all. It only depends on my current estimate and my forward model and my data. And so this equation is what's being implemented by all of these cyan data consistency blocks. And so that's what I was trying to say here, that when I show a data consistency block, I can equivalently represent this equation as a straightforward linear neural network. And so these weights basically correspond to exactly sort of, oops, just can't see my mouse, the linear updates represented by this equation. Does that clarify it a little bit?
Yeah, that helped a lot. Thank you. I missed that. I forgot about the two-part process. So thank you.
Yeah, no problem. Great question. And Mikhail, did you have another question?
No, I just wanted to say I don't see any other questions. So I think we can proceed.
Okay, great. Okay, so on to something that's maybe a little bit more specific to climate science. And that's data assimilation. So this is something that's widely used, again, in a number of different applications, but perhaps maybe the big poster child is weather and climate forecasting. So in particular, the European Center for Medium Range Weather Forecast uses it all the time. If you go to their webpage, they say that in order to make a forecast, we have to know the state of the atmosphere and the Earth's surface. And so when they make their forecasts, they use data assimilation to estimate initial conditions for their forecast model. So basically, you can think about a lot of these forecast models as being giant systems of PDEs. So giant that we can't easily write down that system of PDEs, and there's lots of different numerical analysis and scientific computing that's gone into the different components of this. But to solve the PDE, we need to have a good set of initial conditions, or we have to estimate parameters of the PDEs from observational data. So in this setting, what we would have is that xt would correspond to the state of the Earth's atmosphere and surface at time t. And this is generally on the order of 10 to the 8th in dimensionality. And the observational data that we collect through a variety of air and water sensors and satellites as well would be on the order of 10 to the 6th at each time point. And so depending on what you're trying to do, often data is collected in 6-hour windows. And so data assimilation is a tool that we would use to actually do this fitting. So here's one framework for deploying this tool or for performing data assimilation. We start with something with a state space model. And the idea would be that we've got some initial prior distribution on the initial condition of our PVE, the initial state of our climate system. And according to this model, at each time t, we can predict what's going to happen at the next time using a model of the dynamics F plus some noise with some covariance Q. But we don't get to observe the full state at each time. Rather, we have this sort of inverse problem setting that I talked about earlier. So we measure H times XT plus some noise, again with some covariance. And so this is sort of cartoonishly illustrated below, where I've got observations from a Lorenz 63 dynamical system that I'm saying would represent my state at each time t in multiple coordinates. And you could imagine a setting where you only get to observe some of those locations at each time point. So in order to make good forecast, we need to know what those underlying dynamics are. So if I go back here, I need to know what F is and what Q is in order to make good predictions. But unfortunately, because these models have unknown parameters or only approximate, this can, or sometimes we don't even have models at all, this can really limit our ability to make good forecasts. So in particular, the way that I'm going to cast this is to say that we're going to imagine that our dynamics are kind of the same as before, but I'm going to use alpha and beta to parameterize my dynamics. And we're going to consider the case where alpha and beta are unknown and where we need to estimate them. So I'll emphasize, you can think about this in a variety of settings. Some would be just simple parametric settings, but others might be where alpha and beta could correspond to something much higher dimensional and complex, like weights of a neural network that model the dynamics of the climate. And so from this context, the goal is the following. What we'd like to be able to do is to take a time series of our observations and estimate the dynamical model, basically estimate these parameters, alpha and beta. And we can relate this to what I was talking about earlier in the talk with linear inverse problems, because at each time point t, we have a linear inverse problem, right? Yt is hxt plus some noise. But now instead of thinking about a regularizer that's regularizing the spatial structure of images, instead what we're going to do is we're going to try to learn essentially a form of regularization of the dynamics. So we're going to do some sort of temporal regularization to help us solve these inverse problems. So the general strategy that we're going to do to use here is the following. So we're going to let theta denote all of the unknowns or parameters that we have to learn. So basically alpha and beta from before, and these could be anything from just a couple of small low dimensional parameters all the way up to a huge number of neural network weights. And what we'd like to do is to choose the values of those parameters that maximize the likelihood of our observations. So we just want to do simple maximum likelihood estimation here. The challenge, however, is that in these settings, the log likelihood just generally doesn't have a nice closed form expression and it has to be numerically approximated. And so solving or finding this maximum likelihood solution can be somewhat complex. And so the way that we're going to approach this is first, we're going to use ideas from stochastic filtering, things like the ensemble Kalman filter. in order to help us get this numerical approximation of the log likelihood. And then second, we're going to use tools from machine learning and things that were developed specifically for backpropagation for neural networks, like auto differentiation, that are going to allow us to get really accurate estimates of the log likelihood gradients so that we can learn these maximum likelihood parameters. Okay, so just to sort of provide a little bit of background, let me talk about stochastic filtering and the ensemble-Kalman filter. The basic idea here is that we want to estimate the current state of an evolving dynamical system when we only have indirect measurements. And sort of the poster child for this framework is tracking. So in a tracking setting, the state, the xt, would be your position and velocity at time t, but you would only observe, say, the location at time t, and maybe that with some noise. And so we might want to do something like filtering, where we say, well, given all the past observations, let me try to estimate the true location and the velocity. So within the ensemble-Kalman filter, there's two steps that we go through. So in particular, we're trying to come up with a probability distribution representing all the possible states of our system. And we're going to represent that probability distribution with a number of different samples or particles. So at each time, let's say t-1, we're going to have a number of different particles. So xn t-1 would be the nth particle for time t-1. And so for each one of these particles, and I've kind of highlighted them in cyan here, this is my current estimate of where the object I'm tracking is. What I want to do is I want to predict where it's going to be at the next time. And this is where I use my dynamics, F alpha and Q beta. So this is what I would do if I knew the dynamics and I didn't have to learn anything. And so I would say, well, for each one of these particles, I'm going to predict where it's going to be next based on this model of my dynamics. And then in the second step, called the analysis step, we observe the location and of the object with some noise. And we would use that plus knowledge of what that forward model is to improve our estimate of each one of the particles. So these red particles are what we had forecast in the past, and we can see our forecast was a little bit off. And so we've now used our observations to update it. And these equations might look a little complex if you haven't used it much before, but the key idea here is that this step does not use the dynamics, but rather it's just using our new data and our knowledge of the physics. So we can think about this analogously to what we were calling the data consistency step when we talked about linear inverse problems. So a little bit more generally, what the ensemble-Kalman filter is doing is it's sequentially getting distributions over the state over all of the time where we have data, parameterized by theta, which corresponds to the parameters of our dynamical model. And so we can actually use the particles that I've been talking about here, and in particular, the mean and covariance of that ensemble of particles in order to approximate the log likelihood. Okay, so far, all I've done is I've told you what we would do if we knew what the dynamics were, if we knew what the right parameters were. But of course, that's what we're trying to estimate. So the question is, how can I use this to come up with a good learning scheme? So a couple of years ago, a team presented an expectation maximization approach, where they alternated iteratively between two steps. In the first step, they said, well, given my current estimate of the dynamics and my data, let me use that ensemble-Kalman filter to get this distribution of particles representing the state at each time. And then they said, okay, using those particles, I'm going to write down my approximate log likelihood and then try to update the parameters of my dynamics by just doing gradient ascent on this log likelihood. So this is fine, but it has some limitations. And the key limitation here is that when we, after we compute these particles using the ensemble-Kalman filter, then we treat them as just fixed objects. And we don't really take into account the fact, the very true fact, that they are functions of the dynamics. And we're going to see some empirical results later where we see that that has some pretty serious limitations. So alternatively, what we do is we explicitly treat the particles as functions of the unknown dynamics that we're trying to estimate. And when we compute our log likelihood and its gradients, we reflect this dependence. Now, this sounds very simple and naive and like, well, why didn't anybody do this before? But the problem was that computationally, it was hard. There aren't nice, simple analytical forms for these things, and it wasn't clear how to even compute these likelihoods or gradients that model this dependence. But tools like auto differentiation essentially fill that gap. So if you're not familiar with it, automatic differentiation is a step beyond numerical differentiation. So in particular, it uses compositions of elementary functions with known derivatives, things like sines or ReLU functions or simple linear inner products. And so when we compute when we try to use auto differentiation to compute a gradient of a function, it's just very lean and mean. And at the same time, it can be much more accurate than classical methods like finite difference approximations, which have all kinds of discretization errors. So here's the EM algorithm that I showed you before, and here is our alternative approach. And the differences maybe on the surface look a little bit subtle, but I think the key one is just what I've highlighted in the box here. So like I said, when we think about the EM algorithm, we treat the particles as just fixed things that came out of the ENKF, but are not functions of the dynamics. Whereas we're able to think about the particles as functions of the dynamics and use that to compute the likelihood and its gradient. So we're going to look at some empirical results. And to test this, we generated simulated data from the Lorenz 96 system. So the true dynamics, F star, correspond to a flow map of a vector field described by a relatively simple ODE. And so what I'm showing you here is one realization of this Lorenz 96 system with 40 different channels. And this is a nice kind of test case, mostly because it's a prototypical turbulent dynamical system. And so it's used a lot to assess different methods that might be used in climate settings. And so here I can show you some empirical results. And in this case, we only observe 2/3 of the state variables. We don't get to observe everything. And so we have to solve this, series of inverse problems by learning a good model of the dynamics. And we, in particular, have use a neural network to represent the dynamics that we have to learn. So this parameter theta that we're learning is pretty high dimensional. So I'm showing the results here in two different cases. So first we could compare the blue line and the orange. So in both of these cases, we assume we know nothing about the underlying dynamics. So in fact, I generated my training data and observational data using this Lorenz 96 model, but I'm not using that knowledge at all here. I'm acting like I don't know what the dynamics are, and I have to learn them from the data. And what we can see is that our method in blue gets much better forecast errors than basically the EM algorithm. And in fact, you don't even see a line for the orange. It's way up here because it's just so unstable. And basically the approximation that it's making of the log likelihood is too coarse to really be effective for this problem. In red and black, we basically have the same thing. The only difference is that in these settings, which is maybe a little bit more relevant to a climate setting, we assume that we've got an approximate model of the dynamics, but that it has some unknown parameters or it's off a little bit, so an approximation. And so we're trying to learn a correction to that approximate model. And so you can see in black that we, again, get much more accurate forecasts, whereas the EM algorithm is, again, pretty, I lost my mouse, but pretty unstable. Okay, so that is the stochastic filtering application. And there's just one final kind of inverse problem setting that I wanted to highlight that's got some unique aspects that we haven't yet talked about here. So as I said before, often climate scientists are going to use really complex computational simulations to make forecasts. And these have been developed over decades, and they're very effective. But in general, in order to make them work, we have to have some parameters X, that parameters that I'm going to call X here. And typically we have to learn these from data. So now I'm going to use similar notation, but the meaning is going to be slightly different. So I think about H now as being a model of this, or a representation of this big simulation engine. So I input parameters of the simulation, and I output, say, something like this picture down below, right? Like models of the climate, atmosphere, or ocean dynamics or land variables. So in practice, once I collect a bunch of data, Y, what I need to know is what is the best fit of parameters that I should use in order to make forecasts using my giant computer simulation. So it's similar in that it's an inverse problem to what we talked about before, but now we have a nonlinear forward model. We also don't have an explicit form for it. We can only access it through simulations. And ideally, not only would we get an estimate of the parameters, but we'd like to get some notion of uncertainty about the parameters. So a couple of years ago, or gosh, I guess already 5 years ago, a team at Caltech that included Tapio Schneider and Shi-Wei Lan and Andrew Stewart proposed the following approach. They said, what we're going to do is we are going to try to find the parameters by solving this optimization problem. So it's a little notation heavy, but let me just walk through it. The idea is that these climate patterns can be chaotic. And so just looking at mean squared error can be pretty misleading. And so instead, what we're going to do is we're going to take our observational data and just compute some moments of it, some first and second moments of different variables. And we're also going to compute some moments of the output of our simulator. And we want to make sure that those moments match. And then we're going to have a loss function that's also a function of these moments as well. So this, had a big impact about how to do Earth system modeling in an age of learning and optimization. But it also had some limitations. So in particular, it took some expert knowledge to figure out how to set this up, like what is the right loss function, what's the right moment function to use, etc. And then in addition, when they solved this, and what they used here was something like ensemble Kalman filtering called ensemble Kalman inversion, it required them to run their big simulation algorithm many, many different times for every candidate X or every candidate parameter they wanted to consider. And they also had, because they're doing an ensemble Kalman inversion method, they had to have a prior for what these parameters were. And in practice, setting this prior is pretty challenging, and the method's output changes a lot depending on the value of that prior. Okay, so another kind of baseline that you might consider is just simple supervised regression. So train a neural network that's going to input your data and output an estimate of some parameters. This works okay, but it turns out that we can do better, and we can do things that give us some uncertainty estimates. So an area that's been receiving quite a bit of interest in the community recently is designing what are called emulators. So the idea is that we've got this simulation engine that we're calling H. And what I want to do is I want to train, say, a neural network that's going to mimic that simulator, but be way faster and easier to run. So I take a whole bunch of training data and I train it to input parameters and output whatever this climate simulator would have output, but to do it much faster. And if I can train a good emulator, then I can use this approach like the Tapio Schneider approach that I just described, only instead of using my really expensive simulation system, I just use the emulator. So that's a standard emulation approach, but it's really very hard to use. We worked hard on it and didn't get very far, in part because we're taking very low dimensional data and trying to output very high dimensional dynamics. And it's a chaotic system, and there are just many reasons why this is a giant challenge. So our framework is doing something slightly different. What we're doing is we're saying, look, if I knew a good kind of moment function, or if I knew a good latent low dimensional representation of the climate, then I could just work directly in that space and emulate that space instead of trying to emulate my raw climate data. Now, we don't know that, unfortunately, but we can try to learn it. And so our approach tries to jointly learn an embedding to a low dimensional parameter space together with an emulator. So G here is taking a parameter and mapping it to this low dimensional space. And F is taking my observed data and also mapping it to that low dimensional space. So I can think about this G hat here as saying, look, I know that there's this underlying H, but I don't need to emulate it. All I really need to emulate is the composition of H with whatever maps my data to this low dimensional space. So far, so good. Now I just want to say something totally different, which is that we were able to take ideas that were developed in the context of computer vision to come up with a way to actually learn these two different mappings, this embedding and this emulator, in an efficient and an effective way. So in the computer vision literature, there's a method called CLIP, or contrastive language image pre-training. And what they did is the following. They said, okay, imagine I've got a whole bunch of images and a whole bunch of captions or text. What I want to do is I want to design some encodings of each. And I want to do this in a way so that if I were to have a pair, say an image and a caption that go together, then their encodings are going to be close together. And if they don't go together, the encodings are far apart. So it's very similar to metric learning, which some of you may have played with already in the past, only now we're using these kind of high dimensional nonlinear encoders instead of just simple linear mappings. And so we were able to take this idea and adopt it within our context. And in particular, we were able to have this parameter encoder, G, and this trajectory encoder, F, and we were able to train them with this same kind of contrastive framework. And one of the things that's really helpful about this is that this works even when you have something like chaotic climate dynamics. Because as you can see here, we're not using anything about the mean squared error of our estimate of Y coming out of some emulator, which can be very hard to match when you've got a chaotic system. So in particular, if I know that two different climate simulations in my training set were generated with very similar parameters, then I know that they should be a match. And I can use that to inform this contrastive learning or something like metric learning, even when I've got chaotic data where from a squared error perspective, things look very, very dissimilar. I'm gonna highlight a couple of results then here. So here, what I'm showing are four different approaches. In blue, we have our approach. So we train this network. And then once we have this network, we feed that learned emulator into this ensemble Kalman inversion method that was proposed by Tapio and Andrew. That gives us a full posterior of the parameters. And we can contrast that with the vanilla ENKI method that doesn't do any learning, also gives a posterior, but requires us to run a really complicated computer simulation a large number of times. We also compared with supervised regression and another method from the simulation-based inference community. And what you can see here is that our method in blue consistently does well, and in fact does dramatically better than the method without learning, which was a little bit surprising to us. What was not surprising, which is what we were really going for, is that we're able to get accurate estimates with just a tiny fraction of the amount of computation time. So this approach that we developed, we were able to generate 500 training samples using this giant computer simulation. And we were able to run 200 different test cases, so 200 different estimation cases, and do all of our training. And that whole process took 0.87 hours. And in contrast, this vanilla approach that doesn't do any learning and just relies on the big computer simulation takes 5.5 days. So even when we take into account all the time that we have to spend to generate the training data using our computer simulation, we still have a giant computational win with this approach. And as you can see, we're not really sacrificing any accuracy. So another thing that's nice here is that I mentioned before that these ensemble Kalman inversion methods require us to have a prior of the parameters, and that this method here in red can be kind of finicky and sensitive to the choice of those parameters. And so we found a way to kind of mitigate that problem that I'd like to just highlight here. So in particular, one of the things that I haven't really described yet is that not only are we mapping the observations to a latent space and parameters to a similar latent space and using this contrastive learning, but also inside this system, we've just got a small little subnetwork whose only job is to do simple supervised regression. So just predict from Y what the parameters are. And we saw previously that that's not so bad on its own, but it doesn't give us uncertainty estimates and is slightly worse. So what we find is that this little regression head can play two important roles. So in particular, let's look at this chart. So in yellow, what we can see is how our method would perform in terms of MAPE if we don't have that regression head. And you can see that it's, for the most parameters, the worst of all the methods. If instead we include that regression head and just run our full method, but we use a single fixed prior equivalent to the prior from the Tapio Schneider and Andrew Stewart work, then we get, for the most of the parameters, a big improvement in accuracy. So this tells us, first of all, that trying to do that regression jointly with all these contrastive techniques really helps a lot. That somehow that regression is helping to guide the rest of the learning, even when it's not being used directly. But then in blue, we can see what gets even smaller errors. And this is basically an empirical Bayes framework, where what we do is we train this same system. So it's exactly the same training as before. But then we take that regression head that we learned and we use it to sort of alter our prior before running the ensemble Kalman inversion. And so basically by using that to set the prior, we can be much more kind of robust. We don't have to worry about the finickiness of setting that prior. And across the board, it gives better results. So overall, I said at the beginning that my main claim is that physics-based models can inform the way we think about how to train different machine learning systems, especially neural networks, how we build them, how we train them, and ultimately what we get are systems that are more reliable and I think more interpretable as well. You know, a little bit more generally, I think that this is a subset of the problems that I find to be really interesting at the intersection of AI and science. And this is something that we've been thinking about a lot at UChicago with our partners at the national labs. I think, you know, one naive approach to AI and science is to say, I'm going to take data collected from my science experiment and then just feed it into some machine learning system. And that's very good and important and useful, but not the only thing that we can do. So I think there's a real potential here for using these kinds of methods to really just inform multiple steps of the scientific method, how we construct hypotheses or design experiments or analyze the data that we collect. And this is related, I think, to a recent DOE report that I made some small contributions to that was about opportunities and challenges from AI and machine learning for the advancement of science, technology, and Office of Science missions. And what this report, well, the report does many, many things, but one part of the report that I found that really resonated with me and that I thought was useful was it lays out some of the big challenges of AI in science. And the challenges are not just how to somehow be helpers to the real scientist, but it really outlines some of the main AI and statistics and machine learning questions that we simply don't know how to answer at this point, but are absolutely necessary for really making an impact in the sciences using the kinds of tools that we develop. And it includes a number of different things. I really talked a lot today about incorporating physical models into AI structure and how that can help when we have small or sparse data sets or help us learn surrogates or emulators. But there's really a lot of other things here as well that I think are important. Things like robustness, inference, and calibration. And I know, for instance, Larry did some really interesting work with conformal prediction and predictive inference that I think is extremely relevant. Things like, just being able to effectively handle noise is the bread and butter of the statistics community. And things like active learning or sequential design is really important when we start thinking about designing experiments. And so I think there's a lot of opportunities here. And I just want to close with a very quick plug that we have a new program, a Schmidt Futures Fellowship to basically support postdocs working at the interface of AI and science. And if you or any of your friends are interested in this, we sincerely hope that you'll consider applying. This will be running for the next 6 years. And so finally, I'd just like to call out my students and postdocs and collaborators, and I would be more than happy to answer any questions that you have. Thank you.
Excellent. Thank you so much, Rebecca.